In this lesson, we'll try to see principle of linear impulse momentum and perhaps solve 4 or 5 problems using PLIM. Let us begin by noting that this PLIM is really integration of Newton's second law. This principle of linear impulse momentum is often abbreviated as PLIM. It's really an integration of Newton's second law within certain time limits. This principle is useful in problems involving force, velocity, and time. To begin with, let us see that Newton's second law is F bar is ma bar, which is m dv over dt. Very many times when we know that we are dealing with vector quantities, we omit this arrow bar on the head. This F bar is the resultant of all the forces acting on the object we are considering. That object may be a single object or a system of objects. We can take this dt onto the other side. So F bar multiplied by dt is m dv bar. We note that at time t is equal to t1, velocity is v1. Time t is equal to t2, velocity is v2. If you look on the right hand side of the equal to sign, this m is constant, so take it out of the integral. M times integral of dv. Integral of dv between v1 and v2 is v2 minus v1. So what we have on the right hand side of the equal to sign is m multiplied by v2 minus v1. That is mv2 minus mv1. We take that minus mv1 onto the other side of the equal to sign and write the equation as shown over here. This equation is what is termed as principle of linear impulse momentum. Very often we consider this v1 to be the initial velocity, v2 to be the final velocity. So what we really have here is initial momentum plus impulse of the resultant is equal to final momentum. This impulse of the resultant force may be considered as sum of impulses of all the forces acting on it. So this quantity integral of f multiplied by dt is what is called impulse of the force F. We can at once see that if this F bar is a constant, it doesn't vary with time. This integral, that is the impulse, comes out to be F into T2 minus T1. Thus, impulse has units of newtons multiplied by second. Newton second is the unit of the impulse. If F is not constant, then we need to integrate it between limits. When f is not available as a function of t, but it is available as a graph between f and t, we can compute the impulse as the area under the f and t curve. We can use this equation in either of the x, y or z directions as per the need, in which case we write mv1x to indicate that it's x component plus impulse along x is equal to final momentum along x direction. Again, we may note that we can use this principle of linear impulse momentum for the whole system, or maybe one subset of the system, that is one subsystem, or to one object in the system. In each case, it is a good idea to draw the free body diagram of the system and then proceed to solve the problem. Having seen what is this PLIM, let us try to solve a few problems. The first problem is shown over here. We have one rope shown in pink color going over two pulleys D and C. One end of the rope is connected to the ceiling, The other end of this cord shown in pink color is connected to the mass M subscript B, its weight being WB. This system is released from rest, and we need to find what is the velocity of the block in 6 seconds. That is, t is equal to 0 is the initial condition, t is equal to 6 is the final condition. Because the pulley mass A and this block B, block A and block B are moving, it is a good idea to have some point of reference and then specify distances from that reference. The reference we have chosen is the datum here, the horizontal line passing through the center of pulley C, and distances SA and SB indicate the locations of the pulley D and the center of mass of this block B. Okay. Now it's a good idea to draw the free body diagrams of objects of interest and then set out to solve the problem. To that effect, we'll draw the free body diagram of pulley D. Pulley D is shown over here, and TA is the tension in this rope shown in kind of orange color, and this whole tension in this whole cord is same, of course, assuming there is no friction at point of all the points of this contact angle of wrap. So again, we assume no friction in this angle of contact. With that assumption, tension in this entire rope is entire cord is constant, that we are showing as TB. TB force here and TB force here, and then one tension here are the forces acting on the pulley D. If you come down to this block A, weight of the block is acting down, tension in the rope is acting up. Similarly, if you come to this block B, tension in the cord is acting up and weight is acting down. In situations where you consider free body diagrams of several objects, it's a good idea to have one direction as shown by Y here to be set as the positive direction and then proceed. Later you don't have any confusion on which term is positive and which term is negative. Now if we stop for a second and see how many number of variables we are dealing with in total, we'll see that TB is one variable, VA is the second variable, TA is the third variable, TB is the fourth variable. So there are four unknown quantities in this problem, and obviously we need to have four equations if we were to solve for any one of them. Those four equations are PLIM for block A along y-axis, PLIM for block B along y-axis, there is a kinematic relation, we'll see what it is in a minute, and then FPD of pulley D. This kinematic equation is 2SA plus SB is equal to constant. We'll see in a second as to how we obtained this. All through the movement in the system, the length of this rope going from the ceiling, going round pulley D, going round pulley C and connected to block B, this length of this rope is remaining constant because it's a rigid body. Rigid bodies do not deform or change their dimensions. Now if you consider this length is constant, the wrap along the wrap, the length of the cord in the wrap here is constant, length of the cord in the wrap here is constant. So length of this, total length of this rope L minus this distance minus this wrap minus this wrap must remain constant. What remains after that is this SA plus again SA plus SB. So 2SA plus SB better be constant. With this set out, we'll try to write PLIM for blocks A and B, as shown in the subsequent slide. I've reproduced the free body diagrams that we have drawn earlier so that we can refer to them very quickly in this slide. Both the blocks are initially at rest, so velocity of block A initially is 0, velocity of block B initially is 0, and our time interval is initially time t is equal to 0 is the initial point, time t is equal to 6 is the final time. Let VA and VB be the velocities after 6 seconds. With this set out, we'll try to draw PLIM for we'll try to write an equation of PLIM for block A. Initial momentum is 0 because initially the block is at rest, and then impulse consists of two forces. Impulse is contributed by two forces. One is the weight of the block, second is the tension TA. Okay, weight of the block is 3 times 9.81, and this constant weight is acting for a period of 6. T2 minus T1 is 6 here, T2 is 6 seconds, T1 is 0. So impulse contributed by the weight is 3 times 9.81 multiplied by 6. Similarly, impulse contributed by TA is minus TA multiplied by T2 minus T1, that is 6. The reason why we have this negative sign is we took Y to be positive downwards, whereas this TA is acting upwards. Okay, we need to note this very carefully. If you put plus TA into 6, the problem is going to be incorrect. The solution is going to be incorrect. Now we write principle of linear impulse momentum for block B. Again, initial momentum is 0 because initially block B is also at rest. Then there are two forces which contribute impulse in this case also. One is the constant weight, 5 multiplied by G, that is 9.81, into T2 minus T1 is 6. And then impulse contributed by TB is negative because TB is going up and our positive direction is down, is equal to final momentum. VB is the final velocity, VA is the final velocity. The other equation is kinematic equation, which we differentiate to obtain 2VA plus VB is 0, and finally we have FBD of pulley D. So we have 4 equations, 4 unknowns we can solve for TB and VB. I would encourage you to go through this problem step by step very thoroughly and convince yourself that you got everything right. Try to solve it without looking at this solution, and then if you get something wrong, come back and refer to the solution provided here. With this, we'll try to solve another problem as shown here. In this problem, you have an SUV shown in kind of sky blue color trying to tow a trailer carrying certain load. The mass of the SUV is given to be 2.5 megagrams. Then mass of this trailer is given to be 1.5 megagrams. The traction force developed, which is the cause for movement, is Fd, which is assumed to be constant at 9 kilonewtons. And we need to find the speed of the truck in 20 seconds starting from rest. So our time duration T1 is equal to 0, T2 is equal to 20 seconds, and both this SUV and the trailer, they are at rest, that is their initial velocities are zeros. We need to find out what is the total velocity, that is velocity of this SUV cum trailer after 20 seconds, that is that T is equal to 20 seconds, and also what is the force in the coupling. To solve this problem, we use PLIM for both these put together. That is, in case 1 we consider the system to be assembly of this SUV and the trailer. In the second case we consider only trailer to find the tension in the coupling. We'll do that real quick, and you see that PLIM is really very handy. So for both these together, you have initial momentum. Momentum is mass times velocity. Mass is mass of SUV plus mass of trailer, m1 plus m2, into initial velocity, which is 0 because they are starting from rest, and impulse of the force. There is only one force acting in here. The tension in the coupling here gets cancelled because these two are coupled together. Internal forces do not appear in equations of equilibrium. This impulse momentum is also one equation of equilibrium. So 9000 multiplied by dt, that is 9000 into 20, is equal to m1 plus m2 into v final. Thus we find the final velocity of SUV plus trailer to be 45 meters per second. And then we draw the free body diagram of the trailer alone. If you consider trailer alone, this T is the tension in the coupling that is acting on. Note that this FD is acting on the SUV. Okay, and so for this we write initial momentum plus the impulse is equal to final momentum. There is only one force, constant force acting on the trailer. So T times 20 is the total impulse. Thus we find T to be 3375 newtons. We'll try to solve a few more problems in subsequent lesson, and one problem of interest is shown over here. After you carefully walk through both the problems in this lesson, try to solve the problem that is given over here, which will be very instructive.